Now let's look at some safe dosage questions. Let's look at the first question. They want us to find the safe dosage required for a child with a BSA of 0.28 meters squared if the recommended dosage is 2 million units per meter squared. In other words, we need to find out how many units we're going to give our child who only has a BSA of 0.28. So first we need to write down our known relationship between units and meters squared. As we can see from the problem, there are 2 million units for 1 meter squared. The question is asking us to find out how many units we need to give for 0.28 meters squared. In order to solve for the unknown number of units, we're going to have to multiply our means and our extremes. That means we need to multiply 2 million units times our 0.28 meters squared and set that equal to 1 meter squared times our unknown number of units. In order to get x by itself, we need to divide both sides by 1 meter squared. In doing so, that leaves x units by itself on one side of the equation. Meter squareds cancel out on the left-hand side, and we need to multiply 2 million units times 0.28 divided by 1. When we do this calculation, we see that we get 560,000 units as a safe dosage for our patient. We can also use the proportion method to solve this problem. They want us to calculate the safe dosage for a child with a BSA of 0.28 meters squared. They tell us the recommended dosage is 2 million units for every meter squared. We can write this recommended dosage as a fraction. We would take 2 million units over 1 meter squared. We'll set this equal to an unknown number of units over our patient's BSA of 0.28 meters squared. We then would cross multiply to solve for x. 2 million units times 0.28 meters squared is equal to 1 meter squared times x units. In order to get x by itself, we have to divide both sides by 1 meter squared. That leaves x by itself on one side of the equation, and meter squared cancels on the left-hand side. Now we just need to multiply 2 million units times 0.28 divided by 1, and we can see that it is safe to give 560,000 units to this particular patient. We can also use dimensional analysis to solve this problem. We want to find the safe dosage for a child with a BSA of 0.28 meters squared. Therefore, we're going to start with our 0.28 meters squared. Now, because this medication is in units, we're going to try to convert meters squared into units. And as we can see from the problem, it tells us the recommended dosage of 2 million units per meter squared. We want to put the meter squared at the bottom. That way our units cancel out, and we'll put 2 million units up top so that our resulting answer will be in units. Now we just need to multiply 0.28 times 2 million units divided by 1, and we find we need to give 560,000 units to our patient. The fourth way we can do this problem is by the formula method. They want us to find the safe dosage of a child who has a BSA of 0.28 meters squared. The recommended dosage is 2 million units per meter squared. In this case, we're going to start with our child's BSA of 0.28 meters squared. We then can see that the recommended dosage is based on 1 meter squared, and it's being given in terms of 2 million units. The meter squared cancels, and we're left with 0.28 divided by 1 times 2 million units, and we discover that we need to give 560,000 units to be safe for this child. Let's look at another safe dosage problem. In this case, they're giving us a recommended dosage for a particular medication, and they want to know if what the doctor ordered for a 22 kilogram patient is going to be safe. Let's read the problem. For a child weighing 22 kilograms, the doctor orders Amican 165 milligrams IV every 8 hours to be infused over 30 minutes. The recommended dosage is 15 to 22.5 milligrams per kilogram per day in 3 divided doses. The supply is Amican 100 milligrams per 2 milliliters. Is the ordered dosage safe? And if it's safe, how many milliliters do we give for each dose? In order to see if this medication is safe, we're going to have to compare our order of 165 milligrams to the recommended dosage. Now, they don't give it based on our child of 22 kilograms. Instead, they tell us we have a range of 15 to 22.5 milligrams per kilogram per day in 3 divided doses. In other words, we're going to have to calculate a minimum and a maximum safe dosage for our particular patient. First, let's find the minimum dosage. The problem tells us that we're allowed to give 15 milligrams per 1 kilogram each day. We need to find out the minimum amount of milligrams we're allowed to give for our 22 kilogram patient. We can solve for this by multiplying our means and our extremes. If we multiply 15 milligrams times 22 kilograms and set that equal to 1 kilogram times an unknown number of milligrams. We're going to divide by 1 kilogram on both sides in order to get our x by itself. And by doing this, we can find out that the minimum amount of milligrams to give per day is going to be 330 milligrams. Now this dosage is per day. However, the doctor didn't give us a daily dosage, he gave us a dosage to be given every 8 hours. If a dosage is given every 8 hours, that means it's going to be 3 times a day. If we look at the safe dosage or the recommended dosage, it tells us that this minimum and maximum is per day to be given in 3 divided doses. Therefore, we're going to take the minimum dose of 330 milligrams and divide it by 3 doses. And in doing so, we're going to see our minimum amount to give is 110 milligrams. That means on our recommended dosage, we're allowed to give a minimum of 110 milligrams. We still need to find out the maximum dose. We are going to have to do this exact same process with the 22.5 milligrams per kilogram per day in 3 divided doses. We'll use the same process we did to find the minimum dosage. First, we're going to set up a relationship between the maximum amount of milligrams and the kilogram. We know we are allowed to give a maximum of 22.5 milligrams per 1 kilogram. We're going to set that equal to an unknown amount of milligrams for our 22 kilogram patient. We then will multiply our means and our extremes. 22.5 milligrams times 22 kilograms and set that equal to 1 kilogram times x milligrams. We then can divide both sides by 1 kilogram. This gives us our x milligrams by itself, and we can see that the maximum amount of milligrams we can give per day is going to be 495. However, again, this is a daily dosage, and we need to divide it by the 3 doses that the doctor wants to give it in. So if we take 495 and divide it into 3 doses, we see the maximum amount we're allowed to give per dose is 165 milligrams. We now should be able to compare our order of 165 milligrams to our range of 110 to 165 milligrams per dose. We should be able to see now that our order falls right in between, or right at the maximum of 165 milligrams. Because it's not more than the maximum, we know this is going to be safe to give. So yes, the dosage is safe. Now that we know it's safe, we want to figure out how many milliliters we're going to give per dose. Well, if we look at our supply, they tell us that every 100 milligrams is in 2 milliliters. The ordered is 165 milligrams, and we need to find out how many milliliters that will be. Again, to solve for x, we're going to multiply our means and our extremes. We have 100 milligrams times x mLs equals 2 mLs times 165 milligrams. We then will divide both sides by 100 milligrams in order to give x by itself. Once we perform the calculation, 2 milliliters times 165 divided by 100, we'll see that we need to give 3.3 milliliters.